mix it with acid. Usually we heat the mixture, and then we finally end up with a lot of gaseous products like carbon dioxide or nitrous gases. And we end up also with a clear solution. What we have to consider here is, yes, we need temperature. Temperature is required, and I will explain why we need temperature. The second thing where we have to put a focus on are the gaseous products. So these gaseous products will be later on related to pressure, and I will explain that in one of the next slides. But let's have a look on the temperature. Temperature is the most important parameter in microwave-assisted sample preparation. So what we have to do, what we aim is to reach high temperature. Pressure is also something we have to consider, but this is not that important. With pressure, we just have to cope somehow. We have to manage that somehow. Pressure is not a, let's say, a parameter for the performance of a microwave digestion system. It's about the temperature. We need the temperature for mainly two reasons. On the first hand, we have to speed up the digestion reaction. So it helps us to save time. We want to make it as quick as possible. And the second reason why we need temperature is to improve the digestion quality. Let's have a look on the time savings of temperature. I don't know, most likely you have heard about the Arrhenius equation. No worries, I will not go into much detail of this equation, but what it clearly says is that if we only increase the temperature by 10 degrees, we will double the reaction rate. So that means increasing the temperature will result in an enormous time saving. So you see that in the table below, that if we just go from 100 degrees to 180 degrees, a reaction which will take 8 hours at 100 degrees will only take roughly 2 minutes at 180 degrees. So the time saving when heating up is enormous. The second thing is we have to improve the digestion quality. And this happens because a higher temperature will increase the oxidation potential of the acid. Mainly, we're using nitric acid. Sometimes we also use other acids, in worst cases, perchloric acid, sulfuric acid, whatever. But mainly we use nitric acid, and increasing the temperature will also increase the oxidation potential. There is a nice chart here showing you the residual carbon as a measure of, let's say, the degree of digestion. And you see that this residual carbon decreases with increasing temperature. Less residual carbon means also that we have less interferences during analysis, which is nowadays of, let's say, less importance than it was before, because the analytical equipment which is available today has become more and more robust. But anyway, better digestion will definitely let you have a, let's say, more appropriate analysis. And we also have to consider that when we do not increase the temperature, we cannot compensate higher temperature with a longer time. So this is not working. So we need to have the higher temperature also because the oxidation potential of the acids has to be increased. We want to get rid of any our organic components from the food sample so that just the trace metals remain in an almost matrix-free solution. This is a very old example, but still shows you how the influence of increasing the digestion temperature. This is just 300 milligrams of some lubrication oil with some nitric acid. The whole time was the same, but we had different temperatures. And you clearly see that increasing the temperature also will improve the digestion result significantly. So we could analyze solutions, let's say from 300 degrees onwards. They still could be analyzed, but I would not subject something like this solution at 170 degrees into an ICP system. Regarding temperature, there's also the question, Why do we need microwave heating? Why do we use microwave systems? The reason is clear. On the one hand, microwave heating provides a direct in-core heating. So here on the right side, we have a scheme of a microwave heated vessel, and on the left side, we have some conventional heating. Conventional heating means we have to transfer the heat from the outside into the liquid bulk, but microwave is directly heating our acid and sample mixture. This is what we want to have. This is where we want to have the heat. We don't want to heat any surroundings. We just want to heat our sample. So it's a very energy efficient way of heating a sample. And the second thing I would consider is even more important is the instant on-off mechanism of microwaves. If you switch on a microwave, it heats. If you switch it off, immediately it stops heating. That's a very important feature when we're talking about reaction control. And those of you who already are digesting samples, especially fatty food stuff, they know that fatty samples with nitric acid, they can react quite heavily, quite exothermal when you heat them too quickly. So for reaction control of these reactions, microwave really provides a high benefit. So we apply microwave heating just to reach high temperature. And also let me mention something. Microwave is just a heating source. It's not doing any magic. It's not changing chemistry. It does not allow things which would not be possible in other settings. It's just heating. But as I mentioned, a very efficient, a very beneficial source of heating. Let's have a look at the pressure. Yeah. So our target, we know high temperature, faster digestions, and better digestions. The problem is here that the temperature is limited by the boiling point of the acid. With nitric acid, this is in the range of 120, 130 degrees. So when we want to reach higher temperature, we cannot do that in an open system. We have to close the system. We have to use a closed vessel like a pressure cooker. But when we're applying a closed vessel, yeah, our gases and the temperature itself comes into play because in a closed vessel we are producing pressure. The pressure is coming from the vapor pressure from the acid itself, but it also comes from the gases products we have seen at the beginning. And regarding this pressure, so you know that slide already, gases products producing pressure. We have this relationship, higher sample weight means more gases. More gases mean a higher pressure inside the vessel. So we have to consider the sample weight as an important parameter for digestion when we're talking about acid digestion in a closed vessel. Too much of a sample weight might overpressurize the vessel, for example. The total pressure, as mentioned, is a sum where if you add the pressure from the acids, the vapor pressure, and you have also to add the reaction pressure from the sample. What does that mean when we have a look at the completely closed digestion vessel? When we have a low sample weight, yeah, could be 100 milligrams, for example, and we start to heat, then that means that the temperature will increase and also the pressure will increase. With the low sample weight, we will stay below the pressure limit, so we will reach the desired temperature and our digestion will run at the desired temperature and will be successful. When we increase the sample weight or if the sample weight is too high and we have a well-controlled system, we will also heat, temperature will increase, but we are running into the pressure limit somewhere. And a good system, a well-controlled system, will then ensure that we do not exceed the pressure limit. If we exceed the pressure limit, the vessel might break. But as a consequence, we are not able to heat further. So the digestion will run at the temperature below the desired target temperature. And this means that maybe the digestion will not work or the digestion quality will not be as good as we expected it. So that means we always have to find a compromise between the sample weight. Higher sample weight usually is required for, let's say, to meet the limits of quantification, and a lower temperature or lower sample weight will be required to reach the temperature. So we always have to find a compromise. We made some considerations a few years ago. We had a look at, let's say, a standard 100 milliliter digestion vessel. This is what you find nowadays quite regularly on the market, 100, even 110 milliliter vessels. But what is going on inside such a vessel? And we just assumed a simple food digestion, half a gram of some carbohydrate, nitric acid, 250 degrees. And what we see is that we end up with a pressure of roughly 60 to 65 bar. We also provide a vessel which is able to provide these conditions, so we can make this digestion in one of our vessels. But what we see is 25 bar coming from the sample, 35 bar is coming from the acid, from the vapor pressure, and we also have some air inside, which also contributes to the pressure inside the vessel. But that means if we have to go higher in sample weight, we will not be able to reach the temperature of 250 when we are already running at the pressure limit. So that means higher sample weight will lower the temperature. If you want to apply higher temperature, we have to lower the sample weight. So this is, let's say, yeah, the range where we are moving. And then we thought, what would happen if we could get rid of the reaction gases somehow? If we could remove them, if we don't have to consider them. And this led us to the development of our smart vent vessels. If we can get rid of reaction gases, the temperature we can digest our sample will be quite independent from the sample weight. No matter if you have low or high sample weight, you will always reach the same temperature. You will always get the same digestion result. If you have a vessel which only has to withstand 40 bar instead of 60 or 80 or 100 bar, we can still reach the same temperature. That's great. Then we can make the vessel a little bit simpler, an easier vessel. The vessel will become more robust. And we also don't have to worry about the headspace. Why are we using, or why are so many vessels available on the market with 100, 110 milliliter? Because they need the headspace to take up the reaction gases. If you can get rid of your gases during the run, you don't need large vessels. You can make smaller ones. They are less heavy. They are smaller. You can put more vessels per run, so you can increase the sample throughput. And this is what we finally came up with our smart vent technology vessels. They release these excess gases during a run. This is just a scheme from our latest vessel. You see the vessel body on the bottom. The vessel is closed with a screw cap, and inside the screw cap, this red piece is also made of PTFE TFM, a very inert and very pure material. And so the vessel is just closed. We make the run, we heat, we build up pressure, but the vessel is closed. If we exceed the pressure limit of this vessel, it will open shortly and release the overpressure. And as long as you stay below the vapor pressure of the acid or below the boiling point of the acid, you mainly release the reaction gases and only a very small fraction of acid vapors. So we really get rid of the carbon dioxide and the nitrous gases. And as soon as the pressure has released, the vessel closes again and our digestion goes on, and we are able to reach the high temperature. And we are able to maintain the temperature level quite independent from the sample weight. How would that look? With a small sample weight, well, it looks the same as for a standard closed vessel. We are reaching the temperature and we do not vent. If we increase the sample weight, then again, we will reach the pressure limit before we have reached the desired temperature. But in this case, the vessel just starts to vent, it vents off the gases, and the temperature can increase until we have reached our desired digestion temperature, and we will run, even with a higher sample weight, a very well digestion. So that's the benefit of the smart vent vessels, that we can always reach the most important temperature parameter, the temperature in a digestion. So far for the theory. Let's have a look on the multi-wave family, our instruments, our three instruments, and also some related applications. From the left side to the right side, we start with the multi-wave 5000, which is a, let's say, laboratory microwave system, which can cover various applications. We have a very special instrument, Multiwave 7000, which is more or less a microwave heated autoclave, which provides digestion. It's a completely different approach. I will explain to you later. And we have Multiwave Go Plus, which is similar, at least the vessel similar to one vessel type, which can be used in Multiwave 5000, but it's much smaller and even, I would say, the most simple microwave system available on the market. Let's have a look into Multiwave 5000. I would just like to highlight a few features of the instrument so that you know what's in there, what the instrument can do. And yeah, it has a tilting touch screen on top, so you can move it into the way how you want to see that you can access the instrument control very nicely. There is a home button there that you can navigate easily through the software. We have a release button to open the door. We have connectivity. We have USB ports on the side, here on the back. We have Ethernet connection for remote control of the instrument or to send run data to, let's say, some network share system. We have an exhaust unit because, as I told you, when we release the gases during a run, we just produce gases, vapors, which are inside the oven. And the exhaust unit removes these gases during a run, and it also ensures that the vessels are cooled down quickly when the digestion is finished. In addition, we provide a smart vent detection. So if the venting exceeds a certain level, we just activate the exhaust.
Hello, Dr. Christian. You are muted. Can you unmute your microphone? Thank
Yes.
you.
Okay. What was the last thing you heard?
It's actually the from the beginning of this slide.
Okay. Thank you.
All
I
right,
didn't
thank you.
notice that I was muted. Okay.
It's okay. It's
So
okay.
okay. So again, I will explain some of the features here. We see the monitor here, a touch screen, which is used to control the instrument, which is used to monitor the reaction progress, to send data. So this is really the control center of the instrument. We have USB and Ethernet connection on the instrument on the side and here on the back. So we can even remote control the instrument. This is also a very nice feature. We have an exhaust unit together with smart vent detection. You remember the reaction during venting means that we are releasing gases. So the gases will stay inside the cavity, and the exhaust unit will just draw them off so that we do not get the vapors and the gases into the lab atmosphere. Also, we provide a smart vent detection. You can set a certain level. If this concentration, if this level is exceeded, the exhaust unit is even drawing off stronger so that we can get rid of the vented gases here. The door itself is can be opened hands-free. So you just tap on the door will open. That's a nice feature. If you go to the instrument and you are already carrying the rotor, so you don't have to put the rotor away, you can just tap the door, open it, put in the rotor. It's a very smooth workflow. We like it in our lab. We use it very frequently. The door itself is made of stainless steel, so it's really stable in case something happens inside the microwave. This is not an issue anymore with the smart vent vessels, but it was in past days when we had the completely closed vessels. There was always an issue with that, let's say a vessel could break and you have a kind of vessel breakage inside the oven during a run. The instrument comes with temperature sensors at the bottom so that we monitor and control the temperature of all the vessels. That's very important because the temperature is our main parameter, which gives us the information how well a digestion went. What we also see, we see that on the movie, a smart light. So there is a little light on the door and it tells you the status of the instrument. If it's just, let's say, uh, um, shining in a white way, everything is fine, instrument is working. If it flashes, it means, well, there is some interaction required. So maybe the run is finished, you can go there and take out the rotor. You see that immediately. And if the smart light is flashing red, something happened, the run was interrupted, uh, whatever, you can go there and have a closer look what exactly happened. Okay. Some of the highlights, I will not mention all of the highlights, is Multiwave 5000 is the most versatile digestion system we have available. It cannot only do acid digestion, you can also use it for solvent extraction, for evaporation of acids, you can use it for drying. We have some special applications, the oxygen combustion in there. So this is really a very versatile instrument and can be configured in many ways. What you see here on the picture are two smart vent rotors. We have a closer look at this one later. This is our, let's say, older 8-position rotor, which is completely closed. The standard, the safety standard, is also an important issue when we talk about acid digestion. So all of our instruments, they fulfill a very high safety standard, and we just certify our safety by external testing labs. So we have both the NRTL and the GS sign, which approve some safety. The important thing with these safety certificates is that this is something which comes from an external institute. So we ship the instrument there, they check it, and if everything is okay, then they certify that we are safe. If not, we have to, let's say, improve something, change something until we get these certificates. So this is nothing we certify ourselves. This comes from an external department. What's also important and the real user benefit is the method library. And the method library can be searched via a full text search. And this is something I would like to show you on the software simulator, because when you are, so this is how it looks like. When you want to start on your instrument, if you want to start a digestion, you also have to consider, well, what is the recipe? How much acid can I take? How much sample can I take? What is the program? And here on this system, we have a method section. And we also say we want to access that more frequently so we can put all the functions we want to have on this home screen. So we can configure the home screen according to our needs. And most likely method will be the first one you want to have. When we have a look at the method library, we see that we have certain categories. We have methods for carbon-containing samples, for metals, for petrochemical samples. There also will be something for food, but we don't have to browse the library. We just have a full text search. So for example, if we want to digest something like beans, we just enter beans and then we find, okay, so we have methods for various kinds of beans. So we just tap the beans. We have a method here. Of course, one method can cover different types of beans. We select the method. We select the rotor. If we have more on the instrument, we select the number of vessel and we tap start. And that's it. And then the instrument will just start the run. So we have an immediate, very quick access to getting started. We don't have to worry around with method optimization, with method development. We just have a look on the method library and select one of the particular samples we want to digest. If you just are looking into fatty food stuff, you can also do that. You get a different method. You get the method only for the rotors which are activated on the instrument. The instrument can come with many different rotors and accessories. Maybe I just can show this to you. So here we see the available rotors. We have some of the HVT vessels and SVT. These four rotors are smart vent vessels. We also have other ones, rotor 8, 16 vessels, solvent extraction, some special reactors for mainly synthesis or small vessel digestion and also for drying. So there is a lot of equipment there, but usually you will just pick out the one rotor you have, and then you have access in the method library and only get the methods for the activated rotors. So this is really one of the new features of these instruments, which is not present in any other equipment on the market so far. What is also nice on this instrument is that we have a video manual on board. So of course, every instrument comes with a written manual, but writing and describing is something, showing something is completely different. And what I would like to do now is show you how to digest various food samples with a rotor 24 HVT. This rotor can go up to 200 degrees and vents at 20 bar. So that means we are still below the boiling point of the nitric acid under these conditions, but we can reliably release the gases which are coming from the digestion. So let's have a closer look on this video. I already mentioned we have three types. So these three vessels share the same specifications. They only differ in volume. We have 50 milliliter and 80 milliliter vessel. We have 24 vessels. And in the middle, we have our high throughput solution with 41 vessels. Of course, we cannot mix the vessels in the different rotors, so one rotor type, one vessel type, but basically the specifications are the same with this rotor. We also see a special turntable here for this rotor because this rotor has two IR sensors to monitor the inner and the outer circle of this rotor. During operation, we have a protection lid there so that if we release vapors, these vapors are really drawn off in a controlled way. Again, this is how to prepare the instrument. I recommend prepare the instrument first, then prepare the vessels. In that case, we were just looking for some fatty food stuff because we also have some oil samples and cocoa sample. We select the method, the instrument is ready to run. What we also can do, we can digest various food samples or types of food samples within one run. One sample will be more reactive, it will vent earlier or more than another sample, but at the end, all the vessels will reach same or almost similar temperatures for the digestion. You see that the vessel body is not too heavy, so it can be put on an analytical balance. We can directly weigh in the sample, which is also a huge benefit. So we don't have to put the sample on the weighing paper and transfer the sample then into the vessel. We can do that directly. So we take out the sample. What you also see on this video manual is we also show you a lot of things, how to do it right and what you must not do. Like here, don't put any sample residues on top of the vessels in the sealing area. If you have sample particles between the seal and the vessel, of course, it will not seal. You will release acid vapors all the time, and this is something you do not want to have. And by the way, sample particles may destroy or damage the sealing area. So take care that the sample is really put inside the vessel and that the sample sits at the bottom of the vessel. We even can use different sample weights in this one run, for example. This is the seal. What you should do, inspect the sealing area before the run. Are there any scratches? I mentioned these vessels are very robust, so it's something which will not get damaged very easily. But anyway, check them before, okay? You can put them into the screw cap, for example. You also can handle them individually. When you add the acid to the vessel, then try to rinse any sample particles which are inside the vessel down to the bottom. Yeah, it's done very quickly. What you should have that all the samples are again down at the bottom and mixed with the acid. And then you just take the screw cap with a seal, you close it. Closing of the vessels is very easily. You just have to put the screw cap into the correct position, which is shown here. Yeah. On the left side, it's not closed enough. On the right side, it's closed too tight. But what you should consider with this vessel, when you close it, okay, yeah, that's the second way. We also have a handling tool in case that you don't like the closing of these vessels by hand. I personally like to do that with the gloves. Don't put the vessel back into the rack, put it into the rotor. The reason is that the Teflon vessel is just a pressure vessel in combination with the rotor. It's not stable when it's outside. If you have an exothermal reaction outside, it can happen that it starts to react, that the solution gets hot, and then that you, let's say, soften the vessel and the vessel will not fit into the rotor again. So once it's closed, put it into the rotor. We show the different load patterns depending on the rotor you have. Load pattern is important for symmetry so that the microwave radiation is also reaching the vessels in a, let's say, similar way so that you also get same temperature on every vessel position. So once the vessels are inside the rotor, you just put on the lid, which protects the cavity from too many vapors. This is the door opener, so you can open that very quickly. Insert the rotor, close the door, and tap start. Or as you've seen before, select the rotor and the vessel numbers, and then the instrument is starting. That's it. Well, with the rotor 41, I think we can skip that. We just have to do, we're using the same procedure, but we have to we have to change the turntable. There's a different turntable, but that's detail for now. So we have the standard turntable and the special one for this, but it's delivered. So you put the rotor inside and that's it. The 41 position rotor is, of course, has a higher weight. It's a little bit more heavy. And so we also show you an alternative way on loading the vessels into the instrument. If you don't want to carry a fully loaded rotor, you can do that also in a different way. So you close the vessels first. You don't close them completely. You just close them so that the screw cap is sitting loosely there on the vessel. Then you fill in your vessels so that it's just loosely, and then you just carry the racks to the instrument. Yes. By the way, if you're wondering how to number the vessels, yes, all the vessels have a kind of stamping inside, so you can mark every individual vessel so that you don't mix them up. And what you can do here also on the instrument is you can fill the vessels directly into the rotor without handling a fully loaded rotor. For those who are afraid of heavy rotors, who do not like to use heavy rotors, they just put in the vessels directly into the rotor. Okay, you close them completely and insert them in the correct position. For the 41 position rotor, we also have the option of manually turning the rotor inside the cavity. This is what you've seen before. You can just activate the turntable so that the turntable then turns the rotor piece by piece. Yeah. So you have a very convenient filling inside the instrument, and that's it. You put on the rotor lid then, and again start the run as we've seen before. So, okay. Okay, I think we can skip that. With the 80 milliliter vessels, this is not working. We have to fill them, of course, in the fume hood. So, the second, sorry, once the digestion has finished, so let me check the second one. Once the instrument has finished, we have to unload the vessels. You see that the smart light here is blinking, showing you, hey, I'm finished. In that case, after run, we have to use the door opening button. We take out the rotor and transfer it to the fume hood. You also can take them out individually, one by one, and carry the racks to the fume hood. You unload the rotor, you have the vessels in there, and what you do now, okay, this is how to open. I think we skip that. Just take out the vessels here. It's the same um, procedure, but just the other way around to take out the vessels. I will skip that, sorry. So we carry them into the rack, into the fume hood. So now we have the vessels here. What we have to consider is that the vessels will still be slightly pressurized. So that means we have some gases in there. And so for this reason, we take some paper. Either we use the handling tool. So the paper will just uh, absorb the gases, and then you just slowly unscrew and, of course, point the vessel away from your face. Slowly unscrew, and you will see then that the vapors of the nitrous gas, of the nitric acid or the nitrous gases, will then remove there. We have this yellow brownish gases here. They are removed. You unscrew the cap together with a seal. We usually put the seal just into a beaker. The few droplets which are on the seal just contain acid condensate. And so the acid condensate is something which does not contribute to the analysis. We just are interested in the solution which is inside the vessel. We pour out the solution, rinse the vessel a few times, fill up to the desired volume, and that's it. We can also open the vessels without a handling tool. This is how I usually do it. You just take the paper there, and the paper just catches any droplets and also catches the fumes which are coming out from the vessel. Slowly open that. You see that, you feel that, you hear it. It's a very easy thing. And then you just open and take out the solutions. Maybe you notice the green solution. This comes from the dissolved nitrous gases. It's a good indication. It shows you that you had an excess of nitric acid for your digestion. If the solution is, let's say, only yellowish after run, that means either that you did not add enough acid, or maybe you had too much venting, or in the worst case, you had kind of leakiness. So this is kind of intermediate um, quality control of your digestion. Okay, so far for Multiwave 5000. What I would like to show you, of course, the performance of that vessel. We had made recently a an application report digestion of various dairy products like milk, curd, butter, yogurt, cottage cheese, whatever. And we also added one certified reference material to this digestion, skimmed milk powder with a certified content of heavy metals inside. The dry weight was calculated to have approximately zero point 0.5 grams per sample. So in fact, we weighed different sample amounts up to 4 grams with milk and raw milk, for example. We added 7 mils of nitric acid. We also need hydrochloric acid for complexation of elements, but usually we add a small amount of hydrochloric acid after digestion because hydrochloric acid is increasing the vapor pressure of the acid mixture and therefore reducing the allowable temperature limit. So for that reason, we usually remove the hydrochloric acid. We don't need it for dissolution of these samples. We just digest with nitric acid, and then we add the hydrochloric acid directly inside the vessel, shake it a little bit, and then we transfer the solution, dilute, and bring it to analysis. The program, very gentle one, 190 degrees average. Average means that the instrument calculates an average temperature of all the vessels. That means some of the vessels might be slightly above this temperature, some might slightly below this temperature, but overall, all vessels are running in the range of 190. The benefit here is if one vessel, for example, goes up to a very high temperature for what particular reason ever, it will not limit the temperature to the other vessels. So maybe this vessel will run dry, but you still have your other vessels which can be um, used for analysis, so the digestion will work nicely. We ramp 20 minutes to this temperature. The ramp time usually is the phase where we have some exothermal reactions, and then we hold it at 15 minutes so that we're also able to digest the more fatty samples here. We used the Rotor 24 HVT50. You have seen that already. And we also made that in Multiwave Go Plus because Multiwave Go Plus is using the same vessel type, the HVT50 vessel, but only 12 instead of 24 vessels. But we digested these samples in both of the instruments. What I show you are the results for the Multiwave 5000. The digestions were performed in triplicate. All samples, all sample materials were completely digested. We have a huge concentration range. So we used an ICP MS and also the graphite furnace atomic absorption for the, let's say, lower concentrations in the ppm range, and in the gram per kilogram range, we also used an ICP OAS. And what you see is that the recoveries are excellent for both concentration ranges. So from arsenic to zinc, these were the milligram per kilogram range, and also the higher concentrations from calcium to phosphorus, they also showed a very good recovery then. So this is a clear proof that we do not lose elements when we are applying a smart vent technology, because this is usually one of the first questions. Hey, but if you release the gases during a run, don't we lose analytes? No, if we operate them correctly, we do not lose volatile elements. Let's have a look at the other instrument, the Multiwave Go Plus, the smallest microwave system we have, the simplest microwave system we have, and I think, one of the coolest systems we have. I will explain you why. First, let's have a look at the features. Well, again, we have a touch screen. It's a little bit smaller. Again, it allows you to control the instrument, to see the run data, to see the digestion progress. We have USB interface on top and also at the back of the instrument. We have a safety cover with interlock, so we can only apply microwave when the instrument is closed. We have an aluminum rotor which only has 5 kilograms when fully loaded with 12 of the HVT vessels. We have seen them in the movie, so they're handled in the same way. They have the smart vent technology. They are monitored and controlled by an AI temperature sensor in front of the instrument. Also, this instrument has an integrated exhaust and cooling unit because we have to draw off vapors which come out here, and we want to cool down the vessel after run. In front, we see the open button, which is only accessible when the instrument has finished. The instrument remains locked during a run. It has a very small footprint. It really fits in every lab, I would say, and it's also not that heavy, only 30 kilograms. So even I can carry that instrument on my own. What is really a cool thing about this instrument is the directed multimode cavity, the way how we introduce the microwave to the vessels. With a Multiwave 5000, this one works like a standard microwave oven. You know it from the kitchen, like a kitchen microwave. You put in something and you have the microwave everywhere and the microwave is absorbed. In Multiwave Go Plus, it's a little bit different. Um, you see that here a cross section from the side. Here is the rotor and the vessels. The microwave is coming from the bottom, is guided through the rotor to the vessel. And depending on the filling level of the vessel, the microwave is then, let's say, drawn into the liquid part and is heating the liquid, is heating the acid with the sample. If there is no vessel inside the rotor, the microwave cannot pass through because in air, the microwave, the wavelength of the microwave is much larger, so it cannot fit through there. So there is no microwave emission outside the rotor, and it's really guided directly towards or into the acid mixture we are applying here. So, and this way allows us to build this very compact system with a very efficient heating system. Another nice feature, which I would like to mention here, is the single vessel mode. It can happen that you only have one sample. There are labs which do not have such a high sample throughput. So they just want to have one sample, a few samples a day maybe, or they just want to know exactly what's going on inside this one vessel during a, let's say, method development. And so you just put in one vessel, the rotor is placing the vessel over the IR sensor, and we can continuously control the temperature inside this vessel. So we exactly know what's going on inside. And once we know the reaction behavior, for example, we can make a method for more vessels, or we just digest one vessel after the other. So for those who only have a very small sample throughput, even this system can cover that very easily. We also, of course, are able to digest food samples with this vessel. In this case, we just tested the, excuse me, I have to use a piece of water. We just test the usability or the availability of the instrument to um, digest samples properly just by using certified reference materials. And so we were using these 3 plankton spinach leaves. Oyster tissue, the digestion conditions are similar, 1 gram sample in that case, 1 milliliter of nitric acid, again, some hydrochloric acid we added after the run. We need the hydrochloric acid to stabilize some elements, mercury, iron, for example. They are stabilized by the hydrochloric acid so that it does not absorb to the vessel wall. And the program takes 30 minutes, 20 minutes to 180 degrees, again in average mode. and hold for 10 minutes. And again, here's just the result for the plankton. Um, Again, we see the recoveries are excellent. Yeah, even the indicative values are very nicely. So you see that again here with the SmartVent, we do not lose elements. We really are able to provide accurate results with this system. Last but not least, Multiwave 7000, a completely different instrument, a completely different digestion approach. Also I would say the most sophisticated one. This instrument comes with the pressurized digestion cavity. We call it PDC. This is an autoclave which is heated by microwave from the bottom. And it does not use vessels. It's using vials and racks. I show you then in one of the later slides. So everything is done inside this autoclave. And we just need the surrounding to heat, to cool the autoclave, to control it. So what we see here is we have a lid. This lid contains the pressure lines. The instrument is filled with nitrogen or argon prior to heating to avoid boiling. We have the clamps to close the instrument. We have an automated cover. So when we close it, this is an automated software guided flow to close and also to open the instrument. We have a window shield which protects the user, especially when you open and some vapors come out that you're standing in front of the instrument, that you do not get harmed by the vapors coming out. We have some exhaust on the side to draw off vapors during the opening. We have a touch screen again to control the instrument and to see what's going on. Also, this instrument has a smart light with the same function telling you, hey, everything is fine. Hey, I'm finished. Come open and take out the samples. Or again, when it's red, hey, something happened. Please have a closer look. We have USB connection, Ethernet connection. This instrument also provides an optional steering module, so you can stir during your digestions if you want to do that. And it also has a real analog manometer, just in case that you have a power failure and the instrument is closed so that you know, is the instrument under pressure or not. So this is the main, let's say, feature from the outside. How does it work? I mentioned we just have vials, borosilicate vials from the daily lab business, maybe. You can use these ones. You can use vials made of quartz if you have lower trace metal concentrations. So quartz definitely provides a higher purity. Or if you want to use hydrofluoric acid, we also provide vessels made of PTFE, TFM. We add the sample, we add the acid to the vial, and we close it with a plug-on cap. The plug-on cap is made of Teflon and has a small bore inside. I show you later why this is necessary. And that's it, that's the vessel filling. You weigh in everything, add the acid, maybe mix a little bit, and then you just put the vial as it is into a rack. And the rack depends, of course, on the size of your vials. Larger vials, only 5 vials, smaller vials, up to 28. Usually we run it with 18 vials, so this is main, the main rack we are using. Then we put the rack into a liner. The liner is made of Teflon and is usually filled with some load solution. This is a very diluted acid. So the rack is put into the liner. The vials are immersed in the load solution. So if one vial has a higher temperature, it gets cooled by the load solution. If one vessel is not that reactive, it gets warmed by the load solution. And in addition, all the vials are also heated by the microwave. So with this setting, we get a very high temperature homogeneity, same temperature for all the vessels inside this system. And the liner is put into the autoclave is closed, pressurized, and then we start the heat. Why is it pressurized? This is a vial. This is a symbol, a symbolized plug-on cap. This plug-on cap is open. And at the beginning of the run, we pressurize the system. We apply pressure, 40 bar of nitrogen or argon. This is the standard pressure. And this pressure will also be stay inside the vial, and this pressure will prevent the acid mixture from boiling. So that means we start with 40 bar, then we increase the temperature, and even when we have a higher temperature above, let's say 130 degrees, the nitric acid will not boil because the pressure is preventing the acid from boiling. The pressure also prevents foaming. So if you have samples which tend to foam, this is also something which has which keeps the sample inside the system. Let me show you how this is operated. Again, the handling is very simple. So pressure sealed vials, yes. We call them pressure sealed vials. There is another vial type available. What we do first is we just adjust the pressure line. Usually we do that in the morning. At the end of the working day, we close the nitrogen again. We apply a certain pressure. When we start at 40 bar, usually we go up to 50 or 60 bar. So that works nicely. We select one of the methods. We have generic methods inside this instrument. So just heating programs, the more reactive the sample, the longer the heating ramp, the more difficult the sample, the higher the temperature. Now this liner is filled with 150 ml of water and a few milliliter of nitric acid. We put a O-ring on top. Yeah, again, we show you what you must not do. There should not be any liquid, no droplets on top. So the liner is prepared. Then we can weigh in the sample on the racks. You see here the racks which are available for the instrument. In the meantime, we have two additional new racks. They are not here on the movie. One of the important things is we can digest really completely different samples and sample types within one run, even with different acid mixtures. And we always will get the same temperature. You should not use different acid mixtures in one run during a rotor-based system, because then most likely one of the acid mixtures will go up to a higher temperature, the other will go to a lower temperature, and you will not get the same temperature for all vessels. Here with that system, that works nicely. We provide this kind of a vial holder for every size. You just select the right one, you weigh in again directly on the balance. You can use different vial types in one run. You can use quartz, borosilicate, glass, and TFM. We have a lot of different samples here, like a cold syrup, some tablets, some oil, whatever, everything. Okay, now we do the weighing a little bit more quick. So we weigh in one after the other. If you get sample particles on the vessel wall, you also use the acid to rinse the sample down to the vessel then. Okay. It's a very quick lab worker. What you see here in the movie, this blue gun is an anti-static gun, and it's highly recommended, especially when you use PTFE vials, because especially the powdered samples, they like to become electrostatically charged, and then you get the sample everywhere on the vial or on the vessel, but not at the bottom of the vessel or the vial where you want to have it. So the use of an anti-static device like this gun is really a huge benefit. Again, try to get the sample to the bottom of the vial. If sample sticks to the TFM vial, it can happen that it absorbs microwave energy, that you get a local overheating, and you can destroy the Teflon vial. Luckily, nothing will happen. You will just destroy this vial, but you will not destroy anything else. The other samples will not be compromised. Then you can still analyze them after the digestion. Okay. So once we have filled in everything, we can use a stir bar if the stirrer module is installed. It's not necessary, but for some samples, it's beneficial to use. So you can use them, you don't have to. Okay. Then we add the acid. What we also like to use is a small amount of water sometimes, because the water, that's a general hint, but here we've seen that how efficient it works. A small amount of water can drastically decrease the reactivity of um, a sample during the run. So when you have to bother with very reactive samples, consider the addition of a small amount of water, maybe 1 ml, maybe 2 ml, and so the reactivity of the acid will not be that high, and the run will be much smoother and much safer. Okay, everything is filled. The closing, you see, one of the vials already starts to react. Okay, that's no problem. We close them with the plug-on caps. You see that the closing procedure is very easy. You just put them there on top. Nothing special. You just put them there. That's it. You load the rack. The good thing is you can completely load the rack. You can use 1 vial, 2 vials, 5 vials, whatever you want to do, whatever you have to do. So it's again very versatile. We put in the vials into the rack. We immerse the rack into the liner. Remember, the liner already contains acidified water. We're using this cup to close the liner because now we transfer the liner to the instrument. And this drip cup, we call it, just prevents any vapors coming out while you carry it to the instrument. So the liner is inside the cavity. We remove the drip cup. The exhaust system is either led into a fume hood or to an exhaust system. And then we just start, and the software guides us. It's closing, it's putting the lid on the autoclave. We then close the screws here. We don't have to apply huge force, so this is very easy to do. Yeah, just close it. Tell the software that we finished. The instrument will lock the cover and we start to pressurize. We start with 40 bar, usually by default. Then the instrument automatically takes the desired pressure, fills up to 40, or in that case, it was obviously 50 bar. The run is starting, and that's it. And when the run is finished, the instrument cools down automatically. If the certain temperature, in that case 80 degrees, is reached, the instrument releases the pressure automatically. This is what you see here. And when it's finished, it tells you, and the smart light is flashing. That's it. When the run is finished, sorry, press the CO2 as unloading. Once the run is finished, the instrument tells you what you need is a piece of paper and the drip cup. Check if the pressure is really released. I can tell you so far it was always the case. And then we just make the opening sequence in the different direction than the closing. We open the clamps. We have a special device here so that you really lift both clamps so that the clamp is not sticking to the autoclave. Now we open, you see that some of the digestion vapors are coming out and they are drawn off on the side of the instrument. We wait a minute or a few seconds, depends on. And then we just take the paper and catch the droplets which are on top of the lid. What I also do usually, which is unfortunately not shown here. I take the drip cup and put it immediately there on top so that any vapors which are in there not coming out. We have a liner lift, and let me mention something. It looks like the liner shoots out like a rocket. That's not the case. So once the liner is on top, you see the grooves here. These grooves prevent the liner from just coming out. So it looks like I'm catching it, but it's definitely not the case. Just let me mention that. And then you carry again the liner into the fume hood. You take out um, the rack from the load solution, put it again on the drip cup. The vessels are moist outside. So what I do is I take the paper and, okay, forget about the removal of the O-ring. We can do that later. What I usually do is to wipe the vials off then. The load solution, which we put in at the beginning, consisting of water and a few mils of acid, has to be changed every time. You cannot reuse that. So don't do that. And don't try to save a few milliliter of acid just by reusing that solution. Okay, wiping off. We have numbered positions on the rack, so we know which vial is which one. So we just can identify them. That's important. Just remove the droplets which are on top and on the outside of the vessel. Usually the vessels are a little bit warm in the range of 65, 60, 70 degrees. So they dry rather quickly. We put them into the rack. Again, we have some acid condensate droplets on top on the plug-on caps, but we discard them. We just put them into some water where we rinse them for they're ready for the next use. Then we just dry them a little bit, and then we just start to transfer the solution from every individual vial into some autosampler vial, for example. And the principle is the same. We quantitatively transfer the solution from the vial and fill up to a defined volume, in this case 15 milliliter, but you can also use any other vial you want to use. In this case, we're using 15, and that's it. And you see, again, a nice result. The dissolved nitrous gases are removed or are not visible after dilution anymore, and works nicely. Okay, I think we can stop that here. We don't want to watch all the other 18 vials. What I would like to show you is, again, a result of a digestion of food samples. Again, we have been verifying the performance with the SRMs, in this case, spinach and oyster. We can use up to 0.5 grams in these small vials. In the REC 18, where we have 18 vials, we have 18 milliliter vials, and they can carry up to half a gram of a sample. We have been using a diluted nitric acid, and for some elements, again, we added a small amount of hydrochloric acid after the run again. Why did we do that in this case? In this case, this has nothing to do with the temperature which can be reached. With the 7000, there is a difference. When you use hydrochloric acid, you have to clean more frequently than using no hydrochloric acid, because for the metal parts, hydrochloric acid, of course, is something these parts do not like very much. So it makes a difference in terms of cleaning frequency. We went up to 250 degrees, which is a moderate temperature for that equipment. It can go up to 280 degrees for a few hours. So 250 and 30 minutes heating procedure is really a nice thing. This is how the run looks like. We start with 40 bar in that case. We see that at around 6 to 7 minutes, we have some exothermal reaction. The pressure is increasing. We also see an increase in temperature. What is the microwave doing? It immediately reduces the microwave power and then gently again heats. So everything is under control. We don't know which vial has reacted, but we know that all the vials get the same temperature, and the instrument is just controlling everything so that we go up to the desired temperature, hold it there, and after the run, we just cool down. And when we reached, in that case, 80 degrees, we start to automatically decrease the pressure and the run is finished. And what we see here, what we did in this report, we made two runs, one with the quartz vials only, and one where we mixed quartz and PTFE TFM. Yeah, for the nerds, we have been using ICP-MS with helium as collision gas. What we got, again, excellent recoveries. We did not observe any difference between the PTFE vials and the quartz vials. Why should we? To be honest, both materials are of highest purity. The only thing I would like to add here, this does not mean that we use mercury. The reason was that we did not measure immediately. We collected the solutions, we transferred them to the university where we did the measurements, and at the university they also did not measure immediately. And if you have a digestion solution, even when stabilized with hydrochloric acid, and you do not measure it immediately, you will lose, let's say, mercury uh, prior to the measurement, although it was there quite after the analysis. We've seen that a few times, but we said we still have a recovery which is comparably acceptable. It's in the range of 85% plus minus something. And we know the reason, so we just decided not to re-measure everything, because we know that from other samples, when we measure immediately, we get an appropriate recovery. If we leave it there for a few days, we get recoveries that can go down up to 40-45% with the same material. So this is nothing to worry about. Okay, that's it so far. Just let me summarize most of the important things we have seen here. What I would like you to take home is just to remember that the temperature is the most important parameter for the acid digestion. It's all about the temperature. Pressure is a side effect which we have to cope somehow, but temperature is what we have to care of. Smart vent technology, that means the release of gases, is able to overcome pressure limitations and allows us higher sample weights without, let's say, making any compromise on temperature. That's an important thing. You have seen it's a comparable robust vessel. We don't have any fancy parts there. We just have one comparably robust sealing area. So there's nothing you can do wrong. You just have to assemble 3 parts. So it's easy and robust. And if you want to speed up your sample preparation, the SmartVent technology can help you, because you just go up to your desired target temperature. You can make your digestion as fast as possible. And what you've seen, the multi-wave family consisting of 3 instruments, it provides reliable acid digestion of food samples in different ways. So this is the question of, let's say, your preference, your budget, your sample throughput, whatever. So one of these instruments will definitely be the one instrument which is able to provide a good solution to you. And all of the instruments, they deliver easy and convenient handling, which is relevant, I would say, for on a, let's say, focus on daily business, if you do that every day. And the recoveries are excellent when you have been using the multi-wave instruments to prepare the samples for the ICP OAS. So maybe you want to give it a try, then feel free to do so. Thank you very much for your attention. That was it from my side so far. I'm glad to answer your questions if you have one. Thank you.
Thank you very much, Dr. Christian. It was very interesting and informative presentation and live demonstration. Let me please summarize the session in Arabic in just 1 or 2 minutes. and then
Yes.
I will have any questions from the participants and I will forward to you. شكرا لكم جميعا حضوركم للمحاضرة اليوم، يا رب تكونوا استفدتم. النهاردة كان محاضرتنا عن عملية هضم العينات الغذائية كجزء من السامبل بريبريشن او تحضير العينات قبل الاليمنتال اناليسيز. احنا طبعا ما نقدرش يعني ناخد عينات الغذاء ونستخدمها على طول في الاجهزه زي الاي سي بي او الجي سي او الى اخره، ولكن لازم تمر بعمليه تحضير للعينات. تحضير العينات يعني تحويل العينه الى سوليوشن، وده بيتطلب الوصول لدرجه حراره معينه علشان يتم هضم العينه كليا وتكون جاهزه لعمليه الاليمنتال اناليسيز اللي احنا هنعملها بعد كده. زي ما دكتور كريستيان قال ان اهم عنصر في عمليه هضم العينات هو الحراره. ازاي بنوصل لدرجه حراره معينه؟ كل عينه بيتم هضمها عند درجه حراره معينه، ولكن توجد مشكله في المعادله بين درجه الحراره والضغط وعمليه هضم الطعام. بالنسبة للعينات علشان نوصل لدرجة حرارة معينة لازم شرط من شروط الهضم ان احنا ما نعديش الضغط اللي يكون جوه الفيسل اللي فيه العينة. ازاي ما نقدرش نعدي الضغط ده ونوصل في نفس الوقت لدرجة الحرارة اللي احنا محتاجينها؟ بان احنا نتحكم في حجم العينة. طيب انا لو استخدمت حجم عينة كبير، كل ما استخدم حجم عينة أكبر كل ما محتاج درجة حرارة أعلى إن أنا أوصل لها عشان يتم هضم العينة. طيب أنا بالتالي لو العينة حجمها كبير ومحتاج أوصل لدرجة حرارة عالية، ممكن يوصل عندي أتخطى الضغط المسموح ليا في الجهاز. وهنا يجي دور الجهاز بتاع شركة أنتون بار، وهي مخترعة تقنية جديدة اسمها سمارت فينت تكنولوجي. سمارت فينت تكنولوجي بتتخلص من الضغوطات اللي ملهاش لازمة اللي جوه الفيسل زي الضغوطات الناتجة عن الغازات، فهي بتعمل ريليز للغازات علشان اقدر استخدم اي حجم عينه انا محتاجه، استخدم احجام اكبر، وبالتالي اقدر اوصل لدرجات حراره اعلى بدون ما اشغل بالي بتخطي الضغط داخل الفيسل. وهنا بتيجي براءة الاختراع من شركة أنتون بار، ودي أهم صفة مميزة للأجهزة بتاعتها. ده كان اختصارا المحاضرة بتاعت اليوم، وأتمنى أن أنا أستقبل أسئلتكم سواء باللغة العربية أو الإنجليزية. احنا نقدر نجاوبكم في أي وقت. تقدروا تكتبوا في الشات بوكس، تقدروا تتكلموا. ممكن لو حد عايز يتكلم يرفع إيده ويفتح الميكروفون. ممكن تبعتوا لي على الواتساب أو الإيميل، وإحنا نقدر نجاوبكم على أي سؤال تحتاجوه. any question please. أي حد عنده أي سؤال؟
الو
يس.
دكتور محمد، المحاضرة واضحة تمام إن شاء الله.
اوكي مستر نور، ثانك يو
في
سو
أي
ماتش.
حد عنده سؤال؟
دكتور محمد،
في سؤال.
اتفضل يا
السلام
استاذ
عليكم.
نور. وعليكم السلام، اتفضل.
دكتور محمد، كنت بسأل بس يعني التكنيك ده خاص بالبريبريشن بتاع العينات، شاملة الميت برضو ولا أنا شفت أمثلة على الديري برودكت بس، ولا الميت برودكت موجودة؟
لا احنا بنقدم بس مثال للديري برودكت. هو عرض ابلكيشن ريبورت للديري برودكت، ولكن طبعا احنا شاملين جميع العينات الغذائيه من ضمنها الميت، وطبعا غير العينات الغذائيه. يعني احنا بنشتغل في العينات، جميع انواع العينات اللي بتحتاج سامبل بريباريشن احنا بيتم هضمها بالميكرويف. ولكن كل انواع من العينات طبعا بتوصل درجات حراره معينه بنحتاج لها انواع معينه من الفيسلز والروترز. اختيار الفيسل والروتر احنا بنساعدك فيه لما تقول لنا على السامبل، احنا بنوضح لك بالظبط ايه هي الروتر والفيسل المناسبين ليه.
طيب السؤال الثاني معلش بعد إذن حضرتك، هو بالنسبة
اتفضل.
لعملية دايجيشن مثلا ل 100 سامبل، هل بيبقى
تمام.
الهدف منها بس ديتكشن بتاع الهيفي ميتالز، ولا في اناليسيز اخرى بتحتاج دايجيشن معين بيقوم بيها المالتي ويف 5000؟
تمام. لو لا استاذنك ان انا اترجم السؤال لدكتور كريستيان، بحيث ان هو ممكن يكون عنده اجابه اوضح. لحظه.
تمام.
دكتور كريستيان.
Yeah.
Dr. Mustafa is asking a question regarding the digestion of meat samples. Is the removal of or the quantification of the heavy metals is the only purpose of the elemental analysis of such samples? This is why we are digesting them before the analysis, or there are other purposes or reasons why we are digesting these samples?
Yes. There is. I will switch on my camera so that you see me.
All right.
The main purpose, yes, is the digestion of trace metals when we do this acid digestion. I know that in, let's say, food technology or in food research, we also have a lot of different other parameters we want to measure, like a fat content, for example. But usually these conditions or these methods, they do not need that harsh conditions. So it doesn't make much sense to use a microwave, for example, to do a fat extraction. We tried that with food samples with some partial success, but not complete success. And also for meat, if you want to do other parameters which are related to some, let's say, organic things like organic contaminants, like pesticide residues, I mean, you can extract them. We have some extraction applications for environmental samples, not dedicated to food, but usually what you want to have are the trace metals. This is where a microwave system is perfectly suited for. All the other things is something which we could consider and have to optimize the method, for example. But that's only a small fraction of users who want to do this.
All right, thank you Dr. Christian. دكتور مصطفى، هل كل شيء واضح؟ الإجابة واضحة؟
تمام فهمت.
ممكن أعرف حضرتك من شركة إيه أو من جامعة إيه؟
أنا كلية الزراعة جامعة مصراتة.
تمام. أهلا وسهلا،
ريسك.
اتشرفت بحضرتك.
Yes, sir. Good morning, guys.
Good morning.
You hear me, guys?
I'm sorry, the voice, I don't know whether I have a problem or not, but the voice is not heard well. Can you repeat, please?
Do you hear me, guys?
Yes, I hear you now.
Okay. What about the radioactive material, food that contaminated with radioactive elements? Do multi-wave could do the job for that? This is the first question. The second is to what accuracy multi-wave could reach. The third is, we know food is containing of carbohydrate, protein, and lipid, some of it. So it works with all these constituent, whatever the type of food is.
Okay. Let me start with the first question regarding the radioactive isotopes. In principle, if you can determine your radioactive isotopes after digesting, let's say, 0.5 gram or 1 gram of food samples, you can do that as well because it's an element. You might have some troubles maybe if your element, if you're looking, let's say, something like tritium, which will just be released during the venting action. But if you're really talking about the real radioactive metals, trace metals, you will be able to find them. The only tricky thing can be, I remember we had an application many years ago where the user wanted to determine radioactive isotopes from soil samples, not from food. But the problem here was that the subsequent determination of, I think he was looking for alpha radiators, required a certain high amount of sample because the concentration in the sample was that low. So in that case, we had to combine, we digested, I think, the sample divided to 4 or 6 vessels so that we increased the sample weight. Then we were combining these mixtures. We also were evaporating the acid. So it was a tedious procedure, but finally the customer ended up with a, let's say, concentrated digest of a sample. And this digest was able then to be determined for these alpha radiators. So this is something, if you have to do that on a routine basis, you have to find out if the maximum sample you can digest of your sample is still provides enough sensitivity, provides enough of your radioactive isotopes that you can determine them easily. Otherwise, it will become tedious. You have to digest 2 vessels, 3 vessels, 4 vessels, whatever, and combine the solution afterwards. But in principle, yes, that's possible.
For both gamma and beta.
I'm not an expert on determination of radioactive isotopes, but if what you know is, or what you can estimate, if you say, I need at least 2 grams of sample so that I have enough radioactive concentration, which I can measure, okay, then we just have to find out, okay, how can we digest 2 grams? And this is something like, I would say, on a routine basis, 2 to 4 vessels, depends on the sample and depends on the system. But one digestion of 1 gram could work, but most likely we have to use a little bit less. But then we just digest several vessels so that we have the appropriate amount of sample, the sample amount, yes, and then we can analyze that. That should not be the problem then. Most likely we have to evaporate also, which is an additional step. But if the determination method is, let's say, a little bit tricky, it will also justify a little bit more tricky sample preparation if you don't have any other chance to digest, to analyze these analytes in your sample in a different way.
And your multi-wave system can be, you know, when you work with radioactive materials, you have to be in hood, special hood. It will be installed inside the hood?
Yes,
or
you can install the instrument in a fume hood. Usually we do not do that. We don't want to do that because we want to save the space in the fume hood for other work. But yes, you can put them into a fume hood as well. For some applications, it's already required to put it into a fume hood for synthesis, for example.
Okay, thank you. Thank you.
You're welcome.
About the accuracy? To
yeah.
what concentration?
I remember, yeah, there was. The concentration is nothing you will, let's say, cover with the sample preparation. You know your limit of quantification from your ICP system. So you know which concentrations can I go down. You know which concentration do I expect in my sample. And luckily for food samples, these concentrations are very low. And from these 2 values, you just calculate how much sample do I require so that I, let's say, obtain a solution which is above the LOQ of my system. So it's basically a matter of sample weight, which you can digest in the system, or which you have to digest to obtain a proper analytical result. So this is something an analytical chemist will just calculate from the backend, from the ICP system down to, okay, how much sample do I have to take?
Thank you. Really. Thank you.
You're welcome. Thank you.
Thanks to Anton Bar and thanks to Fatih.
Thank you, Mr. Mabrouk. We have the honor to have you here. And thank you very
Thank
much, Dr. Kristin. We really enjoyed the presentation, and all
Thank you very
participants
much.
are sending their greetings in the chat box. They are thanking you very much. And
Thank you.
please, if you have any questions later, please don't hesitate to contact me in the WhatsApp or in the email so that we can answer you anytime. Thank you all for attending. Thank you again, Dr. Kristin. And
you.
we are going to the end of our session today. And I have to say goodbye to you all. Goodbye.
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 Thanks a lot. Thank you.
You're welcome.
Salut.